They're using a software, commercial software, computational fluid dynamics, but maybe lattice Boltzmann and Monte Carlo method may be an alternative method to work with the same images they are working and do pore scale modeling. So Keerti, you have 30 minutes.
Okay. So good afternoon to everybody. My name is Keerti Sharma, as you can see from there. And I'm very lucky. Thank you. No problem. It's okay. I'm very lucky to be talking in the end because before me, I had many my colleagues and scientists and professors have talked about a lot of different topics about enhanced oil recovery. And we believe that every presentation must have a take-home message and or take-home challenges or take-home problems. What I took from all the presentations by now is the soul of the work that has been presented today lies somewhere in the interaction between the fluid and the rock. The geometry, the complexity, and how the fluids interact with the rock is the main soul of this work has been presented today. So I believe that this pore scale modeling that we are talking about would be very useful in order to at least find some solid solutions for that. So as you can see, I'll start from lattice-Boltzmann methods. Then we will talk about the laboratory validation of these lattice-Boltzmann methods. I will give an insight what it is. And then the alternative options if there's some other solutions we have, some other ways to solve these problems. So what exactly lattice-Boltzmann method is? We can say, what is a lattice? Lattice is nothing. Lattice is just an art. Lattice is a module. Lattice is an arrangement. And Boltzmann is an equation. So here, combining them together, the lattice-Boltzmann method is a class of computational fluid dynamics methods for fluid simulations. Basically, people have a tendency to solve Navier-Stokes equations for the CFD problems, to solve CFD problems. But here we are trying to solve from a different perspective, a different point of view. So the discrete Boltzmann equation is solved to simulate the flow of Newtonian fluid with collision models such as BGK. So we can say that by simulating the streaming and collision process across a limited number of particles, the intrinsic particle interactions evince a microcosm of viscous flow behavior applicable across the greater mass. What it says is that we define the fluid and the porous medium as nodes or lattice points. The pore can be defined as the pore lattice points or pore nodes, and the solid, what we call matrix, can be defined as the solid lattice points or solid nodes. And the fluid itself can be defined as infictive particles. Infictive particle, I mean, they're imaginary or fictitious particles that have a particular distribution function. So in our case, the distribution function is the main point. And the propagation is through the distribution function from a lattice point to the other lattice points. And then the collision comes into the picture when there is a distribution function coming from a lattice point from the pore collides or comes in the vicinity of a solid lattice point. So this lattice-Boltzmann method is a relatively new simulation technique for complex fluid systems. Like I said in the beginning that almost all the speakers here talked about the complexity and the interaction between the fluids and the pores and the granular material. So it's in real life, I would say that the real life is not very easy. It's not as simple as we used to think. Like before, in the conventional solutions of the porous medium, we used to think that the pores is just an arrangement of spheres in the space, and the empty space in between those spheres is called pores, and those solid spheres were called matrix. But it is false. It's not true in real life, and especially when we talk about the carbonates or pre-sal, is extremely complex, and the pore connectivity, the geometry, the hydraulic conductivity of your formation is essentially important to be characterized. So, unlike the traditional computational fluid dynamics methods, like they used to solve the conservation equations of macroscopic properties, like mass, momentum, and energy, Lattice-Boltzmann models the fluid consisting of fictive particles, like I said in the beginning, and such particles perform consecutive propagation through the distribution functions. Equilibrium or non-equilibrium, that I will throw some light on that later. So like Lattice-Boltzmann has several advantages over the conventional CFD methods that I will say what are those, especially in dealing with complex boundaries and incorporating microscopic interactions. Microscopic interactions are the interactions between the fluids, the particles, because it has a particulate nature. The fluid has particulate nature, the model is particulate model. And the parallelization of the algorithms. This equation is the propagation governing equation. This is nothing but just a distribution function of each or a particular lattice node. And this is just a relaxation time. And this is everything in our case. Then I would show how it generates and evolves in a different manner. So basic important points about Lattice-Boltzmann. First, we have to define a lattice. Lattice, like I said, is an art, is an arrangement. It can be cubic, it can be triangular, it can be conical. Basically, what we're talking here about cubic or triangular. It can be multidimensional, two-dimensional, three-dimensional, whatever. So, like I said, in Lattice-Boltzmann, we don't deal with the dimensional quantities. We deal with the lattice quantities or lattice units, I would say. So, what happens with the spacing and what happens with the time? If I have a grid or a window of length, say L, and I arrange n number of lattice points, it can be both the total number of pore and the solid matrix. Sorry, pore and solid matrix points, nodal points. So my space can be simply defined as the ratio of the total length of the domain by n number of the nodal points. In the same manner, my temporal coordinate or temporal space could be defined, interval, what I would say, could be defined simply as delta x, which was the space in between the nodes or the lattice points, divided by simply the speed of sound. Now, that is a very interesting point. In Lattice-Boltzmann method, we deal with the velocity, the speed of sound, the concept. Now, what about the small scale flow? Because we are talking about the pore scale modeling. We are not talking about the thermal and other cases like generally we have in CFD. We are talking about the pore. What about this? Imagine if we are talking about the pore scale, they are very, very, very extremely closer to each other, the lattice points. So if we use the velocity of sound to define our intervals, it would be the interval, the space would be extremely small. So what we have to do, we have to increase the Mach number. The Mach number, as you know, is the ratio of the velocity of the object. In our case, the object is the fluid particles governed by the distribution functions divided by the velocity of sound. This is the Mach number. So we increase the Mach number when we come to a small scale flow, to model a small scale or Poor scale flow. Now what happens with the viscosity and Reynolds numbers? Because we simply just can't increase the Mach number, what will happen? The viscosity would be smaller and our Reynolds numbers would not be preserved anymore. So what we need to do at the Poor scale, in this case, we have to increase the viscosity for our Lattice-Boltzmann model so that we can preserve Reynolds number. So we don't deviate from the principle of physics. That's very important. So this is just an equation that how to calculate your distribution function for each lattice point, like this way. These are the microscopic velocity. And this is the density, this is momentum, and this is the velocity. Now, when I say about lattice points and the fluid particles, propagation of the distribution function, actually each lattice point has a certain density value and a certain momentum value. And these density and momentum, they propagate in the mesh, because in Lattice-Boltzmann, the mesh is propagating itself. That's a key concept. Pay attention to that. So what happened? When these lattice points, these distribution functions are propagating and they are colliding with the neighbors, neighbor could be a solid lattice point. So there is a change in the momentum and in the energy or whatever. So you look for the conservation of the conservation principles in that case. So now this is just an collision operator, the equation that defines the collision operator. Then we have the coupling to the real world properties. What I mean real world properties? This density, velocity, and the pressure. There's one thing very, very interesting about pressure. How do we calculate pressure at the Poor scale modeling if we are not dealing with the Navier-Stokes solvers, the conventional Navier-Stokes problems? Because what happens in Navier-Stokes equations, we use an approach called top-to-bottom approach, top-down approach. We start from a nonlinear partial differential equation. We have a nonlinear convective terms in there that we cannot ignore. So how do we solve the pressure? So to solve for the pressure, we need the Poisson equation. And if you solve the Poisson equation, your data communication has to be global. And it costs a lot in the computational efficiency, and the computational efficiency goes down. That is a drawback when you go for the Poor scale modeling and you use the Navier-Stokes solvers. So Lattice-Boltzmann uses a different approach. It uses bottom-up approach. It approached to the solution of Navier-Stokes by already implementing the solutions it had. So this is the key point. And so what happened with the pressure? Pressure is simply calculated from the state equation. You don't need Poisson equation anymore to solve for the pressure in Lattice-Boltzmann. So this is the method of Lattice-Boltzmann, how it is interconnected with the Navier-Stokes, and how we discretize this, and in which manner it follows. So you see, this is the Boltzmann equation, the simple Boltzmann equation. You use the collision operators, the collision concept, and then this Boltzmann equation turns into a discretization in space and time. After this, it turns into this, and then after this discretization, it turns into Lattice-Boltzmann equation with the collision. So it has two operators functioning at this moment. One is streaming, one is collision. Now, you see, when you take into account the collision between the nodal points or the lattice points, Poor or solid, you directly can approach to the Navier-Stokes equation from this solution. Or if you start from there, like our case, we are working at this equation, because this is our propagation governed equation in this case. So we can do a Taylor-Chapman expansion that is very, very complicated to talk here about. It's very complex. You can approach to the continuity equations that come from Navier-Stokes. So this is how this mathematical relation is established here. This is some discretization of these finite differences using finite difference method. And the simple like way you use the Taylor expansion and Chapman this, and then you define the viscosity and the pressure and the stress tensor. This kind of mathematical quantities that we will need. So this Lattice-Boltzmann GK is the same, the group, the name of the scientist who introduced the collision operator into the Lattice-Boltzmann method. So like I said, this is the propagation equation for the distribution function for the lattice points. And the typical claims, what they say is like, oh, it's suited for flows in complex geometries. Yeah, that's true. That we will prove in the end that how well and how accurate it is. And efficient for complex fluids. That's true too. Because Lattice-Boltzmann take into account the properties, the microscopic properties of the fluids at the pore scale. Easy to vectorize, very good scaling, no numerical scheme, is cellular automata, like you all know that, and easy to program. Programming is not very easy, so I don't agree with this. That easy to program is not easy to program. I have almost 3 or 4,000 lines of code, and it's incomplete. So I won't say that it's easy to program, but it's easier if you want to achieve to a very high efficient results and performance. You have to cope up with that. So does LBGK do a better job than conventional methods? Yes, it does. You can ask me a question in the end, why? I will answer to that. What about computational efficiency? The computational efficiency lies in the distribution function and their propagation mechanism. Computational efficiency can be mastered or manipulated by the relaxation times intervals that we will define when we will be characterizing the boundary conditions for our flow. So some just advantages and disadvantages. Linear and exact advection operator. Advection operator, as you know, is a simple transport phenomena. Conservative scheme for mass and momentum, that's right. No numerical viscosity, that's right too. Disadvantages, conditionally stable. Yeah, that's true, because absolutely, you are right, sir. Spacing. Cartesian stropic grids, yeah, that's true too. Unfortunately, that's true. Inherently transient scheme. I would say why this is true and why it's a huge problem for Lattice-Boltzmann cases. So the computational aspects are basic cells, squares and cubes. We will see later. Coupled space and time resolution that I talked about it, about the Mach number, about the spaces and the time intervals. Convergence properties, yes, because every distribution propagation equation for when we calculate the density and the velocity has to converge. You keep on running a loop in the loop, in the loop, in the loop until it converges. And when it converges below to a threshold value, you say, yes, now my simulation is okay. So, stress tensor locally available. Like we said, that in Lattice-Boltzmann, the data communication is local. In Lattice-Boltzmann, data communication is not global. What is the case in Navier-Stokes? You know? So that's why we have benefit of using Lattice-Boltzmann. No numerical viscosity. Very efficient explicit time-stepping scheme. Yeah, that's right. Its time-stepping scheme talks about what? Talks about the collisions between the lattice points or nodes. Yeah, that's right. This is an important part to talk about, conservative scheme for mass and momentum that I already said it in the beginning. So classical approach, direct discretization of Navier-Stokes equation. This is what we do. Scientists generally or conventionally till today, whoever doesn't want to use lattice Boltzmann, they do these things. Finite volume, finite element, finite methods, spectral methods, these kind of things they use. But the challenge lies where? The challenge lies in maximum cell Reynolds number for Navier-Stokes. You know? Now, coming back to the lattice Boltzmann, standard lattice Boltzmann. It's a decent method. Why it's decent? Because it's simpler to incorporate. It's simpler to introduce to the pores as long as you know how to define very well your mesh. No numerical viscosity, I'm repeating it. Substantial improvements possible. Yes, improved data structure for non-matrix codes. Grid refinement. It's a very good facility that is given with this method. It's a virtue of this method that you can do this very easily. The grid refinement. Second order boundary conditions. Non-equilibrium initial conditions that occurs due to the collisions. Multi-relaxation time models. You also can do that. And adaptivity. It's very easy to adapt. Now it's just simple, some mathematical equations here, the grid refinement here, that I don't have to, the stress tensor that is given there. And just simple Taylor expansion of this PDE. And then you have the linear approximation. Now, the boundary conditions. The boundary condition is the most important part when you are trying to solve your flux or fluid flow in the pore scales. How do you incorporate the boundary conditions into that miniature, that minuscule dimensions? So what happens? Lattice Boltzmann use the no-slip concept. You all know, right? No-slip concept for the boundary condition for the gas, for the automata. So here we will use the no-slip concept. What happens? The lattice point from the pore has a particular distribution function. What is lattice point? Is just the fluid particle at a point having a velocity and having a value of density. When it collides with a solid node or solid lattice point that comes from the matrix, it follows two ways. One, it thinks it directly collides to the solid node and it returns to the initial lattice point. But in other case, we call halfway slip. In other case, it considers, it thinks, or whatever you can say, that there is a boundary, there is a wall at the mid distance of the lattice points, in between the pore and the solid lattice points. So that I will, like you can see, the solid lattice, the pore lattice. The pore lattice governing a density through a distribution function, density and velocity. It will collide, if it collides directly here, it will be the full collision. But it also can think in this way, that it can think that the midway, there's a wall here. But here, in this case, no. In the solid points, solid node, it will have a complete collision with that. Now, the lattice Boltzmann method and pore scale modeling, the core ideas. The hydraulic conductivity and granular materials. What is hydraulic conductivity? Is simple permeability of the particular fluid that you are studying in your pore or in the porous medium. As I already talked about this, the initial attempts were made concentrated on relating hydraulic conductivity to porosity, particle size, distribution, and particle angularity. Like we have a tendency to make everything easy. We make a lot of approximations and we say, oh, this is ideal case and this is this and this and that, and everything, the physical problem turns into a very easier problem and we solve it and we become happy. But real life for carbonates is not that simple. Then there were some researchers, they did some semi-analytical models. What is semi-analytical models? There are some work done in the labs. There were some people who generated a two-dimensional, three-dimensional porous medium through computer tomography. And then they, very simple, the very well pore connections and homogeneous porous medium. And then they incorporated the same porous, the same cubes or whatever, the dimensions that you can say, the bodies, to the lattice Boltzmann. And they try to, not lattice Boltzmann, to their mathematical models, because they didn't use lattice Boltzmann. They used simple, their Navier-Stokes solvers or whatever. And then, area of spheres. Area of spheres is not, I don't agree with that. It doesn't solve our life. Now, derivations of these semi-analytical models, they were based on the approximation of porous structure with the simpler geometries. The challenge is the complex geometries. Like every speaker today here talked about the complexity that they have in the pre-sal. The fluid pore interaction, it's complex. It governs all the petrophysical properties. So you cannot just simply ignore it. And the more recently, models have been presented to represent hydraulic conductivity, permeability, based on numerical solutions, fluid flow at the material microscopic level. Okay, that's okay. That simply Navier-Stokes solvers. Now the recent one. The lattice Boltzmann method is one of the most efficient methods that exists today for CFD. That's true. The conventional simulations that been done before were finite difference, finite elements, finite volume, spectral methods. Like I said, top-down approach. You start from a non-linear partial differential equation. You have convectivity. You have what? Convectivity means you have transport phenomena with diffusion problem. That is what Navier-Stokes equation says. So the lattice Boltzmann method, bottom-up approach. We do the expansion in the propagation equation. There are several advantages, methods over traditional Navier-Stokes solvers. Like I said, calculating the pressure. It's very tedious to calculate pressure when you deal with Navier-Stokes solvers because of the Poisson equations. In lattice Boltzmann, you don't do that. Like I said here, some of the Navier-Stokes solvers obtain the pressure values by solving the Poisson equations. And this process requires global data communication, and that reduces the efficiency of the computational models. Advantages: the boundary conditions are very, very easy to implement in this case through parallel computing. That's true. The method naturally accommodates some of the boundary conditions, like we talk about the wall, the collision between the two nodal points. That's a boundary condition. And such as a pressure drop across the interface between two fluids and wedding effects. This is the petrophysical properties here. The research approach. The two-dimensional and three-dimensional numerical models can be developed. So in this two-dimensional, three-dimensional, there is a terminology in lattice Boltzmann called DMQM. It's, or whatever, vice versa, DMQM. It's n dimensional, m velocity. So you can generate your own arrangements or our own module by using this terminology, D and QM, is like two-dimensional with 9 velocity, three-dimensional with 15 or 19 velocity, depending how many resting particles and how many moving particles you are considering. Do you get me? So what I will talk here are two cases, are D2 Q9 and the other one is D3 Q19. So I am dealing with the two-dimensional case with D2 Q9 and I am dealing with the three-dimensional case with D3 Q19. These are called the very basic Lattice-Boltzmann models. Okay, so this is what we will do in the next slides. So these models were used to simulate fluid flow in simple as well as complex geometries. That's what we want. We don't want to think about simple anymore. We want the solution for the complex problems. The porous scale monophasic flow of Newtonian incompressible fluid through porous granular materials and asphalt specimen. But let me tell you very explicitly that we also can solve for the multi-phase flow. And I will say why and how. Next, X-ray computed tomography, like I said, X-ray CT scan, is used to acquire real three-dimensional porous structure of the granular materials, which eliminated the errors associated with assuming idealized porous structures. Because idealized porous structures were simple, some cones and some cylinders and some spheres arranged in the space. But in carbonate, it's not the case. So it's better to look for this technique that William is working, and he is having good knowledge about this. It's very important to have this X-ray CT. The accuracy of these models was verified in the lab with the existing analytical solutions. So how do we do the simulation and this Lattice-Boltzmann programming or whatever you can say that? In 3 phases. The first phase is the initial conditions of the simulations when you set them. What is the first phase? What does it mean, initial conditions for the Lattice-Boltzmann? Because here, like I told you, we are dealing with non-dimensional quantities, units. Our space, time are all lattice units, you know. This is initial condition, I would say, that equilibrium and non-equilibrium properties of the distribution function. So I would say that in the beginning, the distribution function, equilibrium, and in equilibrium has to be equal. Because, why? Why is that? Anyone can say, why is that? Initial condition, because there is no collision. Now the phase 2, the propagation of the distribution function to the neighboring nodes and the collision process are performed. So first we define the distribution function, then we start the propagation, because we have to propagate with some body. And what we propagate with is distribution function. And then the phase 3 is simply assigning boundary conditions and the calculation of the new distribution functions, and that's how we proceed in these simulations. This is the flow chart. Assign density and velocity. Like we already have talked about this, the velocity and the density. We have the propagation equation. We impose the boundary conditions. We come back to the density and velocity again. New density and velocity for what? For the neighbors, for the next lattice points. Velocity is converged? Yes. Terminate the program. It's perfect. Beautiful. Doesn't converge? Go back to the, recalculate the distribution function, and then go back to propagation. Then come back to the same way. It's very interesting, but it's tedious, but it's interesting. So this is how it looks like. You know, this is D2Q9. This is D3Q19. Two-dimensional, 9 velocities vectors. Three-dimensional, 19 velocity vectors. What about the computational efficiency? Let me tell you. It depends on the relaxation time. You put your relaxation time in the simulations equal to unity, you will have very extremely high computational efficiency. Why? Because the distribution function after the collision would be exactly equal or similar to the before collision. This is simple migration of these distribution functions. That's how we do. This is 2D case, because it's extremely difficult to plot or to generate this diagram or whatever for D3Q19, because there's a lot of velocity vectors and a lot of lattice points, and you have to connect each and everything to the neighbors. And one more thing, let me tell you that a lattice point has distribution function values, but not when it is in the neighbor of the solid lattice point. Okay, because of what? Because of the collision. Now, this is very interesting, the boundary conditions. Now come back to the real life, right? It looks like more real, because till now we are talking about mathematical equations and talking about the operators and all these things. This is the porous medium. This white voids is the pore. These blacks are the solids, or you can say matrix. Now just take a small fragment or a part of this, magnify it, it will look like something like this. So what it is? This part is the solid. Solid is this, if you can see exactly, is this. This is step, inverted steps. This is this. And this, whatever is white in this rectangular, inside the lines, is this. What it is? Pore lattices. What it is? Solid lattice points, or solid nodes, or pore nodes. Now, this is the real picture. There are the collisions from the pore lattice to the solid lattices. And each and every nodes or each and every lattice point has its own properties, its own velocity vectors, values, and density. So this is what we are. And what happens? The boundary conditions. If you see, if you check on the inlet, the top, the bottom, the outlet, you would see that the point here, the lattice point here, doesn't have the distribution function for these positions. You mean at the boundary. So you see, the lattice point doesn't have the value of distribution function at the boundaries. You see, all. So what do? You cannot proceed unless you calculate this distribution function. Now you go back to your propagation equation and you use these relations to calculate the distribution functions for each lattice points. Okay? Now, just phase 3. Like I said in the flow chart, check for the convergence. It converges, the velocity, density values converges, perfect. Terminate the program. It doesn't converge, go back again and again and again. Look for the solutions and then propagate again. So this is a simple explanation. Now, how do we know that whatever we did till now, or by now, for D2Q9 was correct, was verified some way? So, this is a scientist, Vanier. He has done some analytical work, and he also has done this lattice-Boltzmann method approach. So what it is? A cylinder of 20 millimeter diameter placed 35 millimeter far from a moving plate. And this guy calculated this flow in the lab on a 70 by 70 window. So you see, these red lines are the streams, how you say, streams of velocity vectors, because the velocity vector streamings are the tangential to the velocity vectors. You will see they're perfectly coinciding. Do you agree? You see the lattice Boltzmann and the Wannier, extremely, hugely in agreement with the analytical solution. But the only difference was that the geometry that he used, DTQ9, was rather simpler. He didn't incorporate the complex geometry of presa like carbonates in this case. Anyway, we will do that. Now the verification of D2Q9 models. As you can see, we used a 280 by 280 lattice resolution was used by Wannier. And see, this is the root mean square error plot. What do you see? It clearly shows that the more lattice points I put into my window, the more efficient my simulations would be. Why? Because the more efficient the propagation of my distribution function would be. Do you agree? And that's how, when you increase the number of lattice points, you see the error goes down. That's magnificent. That's beautiful. Now, just coming to the end, the verification of D3Q19 model. The differences, two-dimensional, three-dimensional. In the two-dimensional case, we didn't need the Poisson equation law to calculate the velocity. But in three-dimensional case, we will need it. So the velocity distribution of laminar flow, we use this equation. The flow through a 10 millimeter diameter circular tube was simulated using this lattice Boltzmann method with a pressure gradient of 10 to the power minus 6. Velocity values at the inlet and the outlet were computed using the equations given on next slide. What are these? Like I told, on the boundaries, a lattice point doesn't have the distribution function. So you have to recalculate them by using these relations. Okay? And the simulations were carried like we carried them for two-dimensional case. See the beautiful results. What are these? The simple node numbers. 10, 20, 40. And this is what we say the Poisson equation or law. We calculate the velocity in the z direction. See the strong agreement with lattice Boltzmann. Check it with Navier-Stokes. You won't get it. I'm not challenging, but I'm just telling what I feel after all this literature and review of literature and these analytical solutions that are available in the books and journals. And see the root mean square error, it governs the same principle. You increase the number of lattice nodes. You increase the number of nodes or lattice points, whatever you say, you decrease the error. You reach closer to the perfection in your simulation by increasing the node. Because just the soul is where? The soul is the distribution, function, propagation. That's it. The more you understand your distribution, function, propagation, the more efficient and more reliable your simulation would be, and the more efficient your understanding about the interaction of fluid and your porous medium would be. Thank you very much. That's it.